Okay, welcome back, folks. This is section 6-2. This is video number 1, and just for the record, chapter or section 6.2 is applications of the normal distribution. Now, listen, I think I'm going to do something a little bit different this time. Let's see how this works out. The electronic version of the book kind of has some errors. It's awkward. It's kind of hard to bounce around in there. So what I'm doing is I am using the PDF version of the text that I sent out to some of you folks. This is edition number 9, so it's not particularly old. Some of the problems are slightly different. Some of the examples are a little bit different, but it won't kill you to see some different examples in addition to the ones that are in your edition number 10 textbook. So let's see how this works. Hopefully make things a little bit easier for me bouncing around between different areas of the text. Okay, so 6-2 is applications of the normal distribution. So in section 6-1, obviously we discussed, what's the normal distribution. And we also talked about how the normal distribution can be considered as a probability distribution. Okay, so the first part here, the author always tries to give you a little bit of motivation. And I agree with everything he says. It's a very, very important distribution. Now, one of the key things here that I think is important to stress is that we can use the normal distribution even if the variable that we're talking about is not normally distributed. Now, obviously, if it's normally distributed, that's great. But if it's only approximately normally distributed, you can still use it. It's such an easy distribution to do the calculations that many times we make that assumption. However, you can't get crazy about it. Okay, you can't be a scientist and just do things outlandish techniques. So here's a sentence that talks about that. There are several tests to determine whether a variable is normally distributed. Okay, so I want you to be aware. I don't think we're going to actually have any problems. There may be something in the quiz, but in the chapter quiz for homework. But I'm not going to test you on this because that's a little bit more specialized than we really need to get into. I just want you to be aware, in case someday you are doing this for a living, I need you to be aware that there are tests that determine whether or not this distribution is appropriately used. And we'll see that, okay? But we're not going to do any exercises or it won't be on the exam. Okay, so what he says here is, okay, so for our problems, you can assume that a variable is normally or at least approximately normally distributed. Okay, so let me spend a little bit of time on this, talking about this transformation. In mathematics, transformations are very important. A transformation goes from one set to another set. And the idea is that you do this transformation for a variety of reasons. For our purposes, what we're trying to do here is we're trying to transform from the original data points to the z-scores or the z-values. And the reason we're doing that is because whatever we decide, whatever conclusions we reach, when we're in the z variable space, those evaluations, those decisions, those answers are going to be useful back in our original data space. So I think the best way of thinking about this is you've got the original measurements in one set, one space, and you have the z-scores is the other space. You're going to be doing these transformations. You're going to go back and forth between the original data and the z-scores. And so how do you do that? Well, here it is. To transform the original variable to a standard normal distribution variable, here's the formula. The original value, okay, and we'll see an example here in just one second. The original value here, for example, and I think the very next example, we're talking about liters of blood, okay? So X could be how many liters of blood does each of your test persons have. So the value is the original value, liters of blood, okay? And you subtract the mean. Well, the mean is the the mean of the original distribution, okay? The original distribution. And then you divide by the standard deviation. Well, that's the standard deviation of the original distribution. So what it boils down to is that you've got these values that are in the original measurement space, the original measurements. You do some calculations on them, then you do this transformation, and miraculously you get a z-score, and the z-score is described in the tables in the back of the book, and any decisions that you make about the z-scores are equally valid about the original data scores, or the original variables. Okay, and that's what he's saying here. I tried to make it more clear, but I think he did a good job writing this. It's the same formula we used before. This formula transforms the values of the variable, the original variable. They get transformed into standard units, otherwise known as z-values. Other authors will call them z-scores. Once the variable is transformed, once the x, the original x is the original guy, once the original x is transformed, then we use the procedure table, and table E in the appendix can be used to solve the problems. Okay, so I hope that's clear to you, and here's an example that he's going to give us.